Hello, welcome to the week 9 of problem solving session for the NPTEL course on computational complexity. So, last time we saw this class called P slash poly, and and we saw several equivalent definition of it, which is this is also same as the class called P size. So on one hand, we say that P/poly is the set of all languages such that there is a deterministic polytime machine for L given a polynomial sized advice H. And this H is a function from 0 1 to the n to 0 1 to the p of n. Or rather it's a function from n to n, that's what I'll call it. So basically what we said was for a given length n, there will be a common advice that goes through all of them. So and on the other hand, p size is the set of all functions f such that there is a polynomial sized circuit computing f. And we of course know that there are functions that are outside p size because of the counting argument that there exist f which are not in p size. This is by the counting argument that the total number of functions that are possible is 2 to the 2 to the n. Whereas if we count the number of circuits of polynomial size, that is a single exponential in n. So clearly there are lots of functions that can't be computed by poly-size circuits, and this is an existential statement in the sense that we know there are hard functions, but we don't know an explicit hard function. That is you can't describe the function. All we know as of now is that it just exists, and this is one big open problem in the area of complexity. To find this, these are called these are called the explicit construction problems that find an explicit function f from n variables to one variable such that f requires size let's say 2 to the n by n. And so we do know that there are functions of this size. We don't know how to find them. The most explicit the largest explicit function that we know which has a lower bound is something like little o of 5n or something like that. So there's a huge I should call it omega 5.
So this thing is not clear.
Which part?
So in this example, so we are looking for an explicit function, and such that f requires this much size. So there could be many functions, and which would be requiring this size. And so I have problem here that why to give a specific size only. Does this have any relevance, or is this it's a question only? And what would be the implication of having a circuitry of the given size? What would that be?
Okay, so okay, so this problem of okay, so one thing is that we know that there are several of them. Outputting any one of them is fine with us. I mean, okay, and the other thing is why is this important? Because there are several conjectures, such as, I mean, let's say BPP equals P and so on. Okay, so there are several conjectures that we don't know, and there are different approaches that we have over a period of time, that people have tried to come up with. How do we attack this problem? And some of these approaches require as in there is a series of steps that would imply, for example, BPP equals P, but or separation, we don't know. But the step where this fails is that it somewhere uses the fact that we do know such a circuit explicitly. So if we had that circuit explicitly, then we could use it to come up with a game, or I mean communication game and so on. All these protocols, I mean, this is just one approach, for example. So um, although I can't give the exact details, but the point that I'm trying to convey is that several conjectures that are out there, which we care about because they have implications, have approaches that sort of use this explicit circuit, which we don't know as of now. If we knew that, then this approach would have worked and we would have answers to several conjectures, because the approach uses it explicitly. For example, you can so there is this communication complexity that you might have heard of. um,
Yes, but not in detail, not in detail, and probably this would be covered in the coming lectures, I guess. The communication
okay, I see.
complexity.
Okay, so probably we can discuss this thing in detail that time. So basically, the main thing is that from these circuits, so there is an equivalent notion that from certain communication complexity protocols. So what is the hmm. So what is the main idea here is that Alice and Bob, they want to compute something. So maybe um, okay, so they want to compute something, and let's say f of x, and Alice has a part of information, Bob has a part of information, and now they want to exchange several bits back and forth, and at the end of the day they want to find out what this value is. For example, one example would be equality problem, which is Alice has a string which is n bit length, Bob has a string which is n bit length. Okay, and the question is, check whether x is equal to y. Okay, so what will happen here is that one trivial thing that you can think of is probably that maybe Alice sends um, her string sends x to Bob. Now Bob has x and y. This, and Bob can now do some computation and see whether x is actually equal to y. If yes, then maybe Bob sends one to Alice, and if no, then Bob sends 0 to Alice. Okay, so this is just one simple protocol where both of them are allowed to do some exchange of bits, and the goal is to minimize the number of bits that are used. For example, here, how many bits did we use?
So in this case, Alice would be. So your question is, I mean, how many bits? So there could be many strings which Alice has of the length n, or is there only one
Huh.
string?
Yeah. So Alice has one string and Bob has one string.
Okay. So in that case, the Alice would be sending n number of the bits to the Bob,
Right.
and even will that work if Alice sends only half of the bits? No, that won't work.
Hmm.
We require all n number of the bits. Yes.
And Bob sends one bit eventually. Once you figure out whether they are equal or not, one bit is enough to tell Alice um, whether the strings are equal or not. So why is this step needed? Because we defined the problem such that at the end of the communication, both of them should have the answer. So if step 3 is not done, then Alice doesn't know the answer, only Bob knows. And this thing is something that they have already agreed upon. So Alice knows beforehand that if Bob sends a 1, um, in step 3, then that means that the strings are equal. If Bob sends a 0, that means that the strings are different. So there is some kind of protocol that they have agreed upon already, and this communication that happens between them, these are called transcripts. So the things that were exchanged, these are called transcripts. And so this thing that we described is a protocol. Okay. Now, now why are we going over this? So I'll maybe not get into the details, but I'll just give a brief idea. So what happens is, there are problems for which, if you have a protocol, okay, this protocol, you can convert it into a circuit. Maybe this is something that will come up later. We can convert it into a circuit, and vice versa. Okay. So okay, so now the point is that uh, there are several approaches where, if I could have this circuit explicitly, then I will have an explicit protocol. And now once I have this protocol, I can use the bounds that we know. For example, equality requires n bit. So this is a proof that we did not do, but it can be shown that equality requires n bits of communication at least. Okay, or exactly.
Uh, I have two questions here. So in this protocol, number one, who is going to initiate the process? And second thing, I mean, how this entire protocol, this thing, is different from the interactive proof systems. So in the interactive proof systems also, I mean, some kind of interaction is allowed in between the parties, in between the Turing machines, and moreover, they do have the shared resources as well, similar to this one. Probably here also the Alice and Bob must be maintaining some kind of the blackboard. And quite possible that the Alice, instead of sending the bit directly to the Bob, may write that bit there over the board. And probably that kind of the mechanism can also be figured out. So how does this differ from the interactive proof system?
Hmm. Okay. So in the IPs, what you have is, you have two parties, and you also have some additional resources. Um, for example, you have randomness as a resource. So you'll decide. Hmm. Okay, so you have randomness as a resource. Furthermore, yeah, you can change these parameters, whether the verifier machine is allowed to be deterministic, and how much time is it allowed. So based on these several things, we'll put those languages into the classes. For example, if it uses r of n many bits, um, and it's allowed to be, the verifier runs in p of n time, and so on. So based on these, we classify the languages parameterized upon this, whereas what we described just now is just a game, and this can be thought of as a resource. That is, I mean, we didn't specify the time that was needed, or the yeah. So all these parameters are something that we didn't worry about when we defined the game. So this is just a complexity measure, similar to time, space, random bits, and so on. This is called the communication complexity, or the number of bits that are being exchanged. So um, like, we want to minimize the time, we want to minimize the space. Similarly, we want to minimize the number of exchanges that happened and still come up with the correct solution. So whereas what IP is a computational complexity class, because there are several parameters that we define, that within this much time, with this much randomness, and so on, all these parameters, what are the class of languages that can be computed. um,
So if randomness is not allowed in the IP, then we can think of that NP would be the if randomness is not allowed, then NP would be same as IP. Otherwise, NP would be the subset of this.
right.
But at least we can correlate the existing time complexity classes with this IP classes, etc.
Right, right.
However, in the case of the communication complexity, this seems slightly different. Different in the sense that now I cannot, connect this communication complexity with the complexity classes I have already studied. I mean, the classes which we have studied so far. So, because in this case, if it is just a matter of that how many bits have been, exchanged, so then bits would always be exchanged equal to the size of the input. So, where is the interestingness in this complexity class?
Okay, so this is not a complexity class. This is a complexity, you can think of this as a complexity measure that we want to minimize.
Oh, I see. So there must be complexity classes under this. I mean, within the purview of the complexity communication complexity as well, similar to NP or P or P space, like in
You
the
can
space.
define it that way. You can always say that what are all the functions, or the problems that are solvable when, say, polynomial many or logarithmic many bits of exchange is allowed, and so on. Um, but the way we look at this approach, or this communication complexity, is as a technique, or one way is that it is viewed as a technique to solve problems, show lower bounds, and so on. The other thing is, you can think of it as a complexity measure. So as such, we don't define, you can always do that, you can always define classes based on how much bits of communication is required, but um, at least as far as I know, such classes have not been defined, because we want to view it differently.
Okay, okay.
Okay, but I'm not sure if that has been done or something. So at least I'm not aware of. And uh, what is the other? Yeah. So to answer the other thing, that in this case, it so happens that n bits of communication was needed, but there could be problems where something much less is also enough. For example, let's say the question that we want to solve is of parity. That is, Alice gets one string of length n, Bob gets another string of length n. They don't know each other's strings, and you want to find out whether um, x uh, parity y, okay, I'll call it parity of x you want to check whether this is 1 or not. Okay, so first take a bitwise parity of Alice's string, take a bitwise parity of Bob's string, and find out a parity of both of them. So trivial thing would be maybe that Alice sends her X to Bob. Now Bob is going to compute the parity, and if it is 1, then send 1 to Alice, otherwise send a 0. Okay, so this is very similar to the previous protocol where Alice sends out her entire string, Bob does the computation and lets Alice know what is the correct answer. But do we really need Alice to send the entire X in this case?
So Alice does not need to send the entire, but then bit by bit, bit by bit. So whether it is one or no. So uh, that would mean that. By the way, what's the meaning of these notations here? Because this XOR.
So yeah, so parity of X is do a bitwise parity of X. So for example, if it is 10110 and this is 11000, then parity of X here is 1 because we are doing basically bitwise parity. So in this case parity of X is 1, parity of Y is 0 because there are even number of ones here, and then basically do a parity of both the answers. These are just 1 bits.
So parity of this, I mean, would be one only if uh, one of them has the odd parity and one has the even type. So uh, and this Alice is sending SX, so this stands for what?
Sorry,
Alice is sending what this SX. You wrote something. I mean,
sorry,
below this.
sends X.
Okay, okay, I
Sorry.
understand. So Alice sends X. Um, so then in this case also, I will be requiring both the strings. Otherwise, Alice computes the result and send the parity to Bob, and then Bob will compute the parity of its own sequence, and then finally display the result that the result is.
Exactly. So you don't really need to send the entire X. What Alice could do is that she could first compute. Alice computes parity X. So this is 1 bit of answer because it's just the parity of the number of ones there, and then Alice only sends this answer parity X. So this is going to take 1 bit of communication, and what Bob will do is Bob will independently compute parity of Y. This is this need not be communicated. Then Bob computes parity X that Alice had sent parity with parity of Y which Bob computed, and this is again a 1 bit answer, and Bob will let Alice know. Yeah, this is another 1 bit of communication that Bob sends. I'll call this B. To Alice. So how much communication did we do all together? 1 bit that Alice sent and 1 bit that Bob sent. So from n bits of communication, we got all the way down to 2 bits.
It's okay. It's okay. So in the communication complexity, probably we are looking for those problems wherein a kind of collaboration is happens. Number one, And second, that we need to identify that probably we need to identify that what are the most interesting and the most crucial part of a problem which need to be communicated to the other parties. And the communication of those crucial results would contribute to the communication complexity of the problem. Like in this case, getting the parity can be done locally. Getting the parity can be done locally. So whatever can be done remotely. So probably in a problem, while determining the communication complexity, we try to identify that what is that interesting part of the problem which needs to be communicated remotely. Is this the case here? Because here two kind of the calculations are being made. Something which is local and something which is remote.
Hmm.
So yeah,
Hmm.
like in the many of the programming problems also, many a times we need to we call an API or
Hmm.
we call a remote procedure.
Hmm.
So probably the communication complexity contribute to that. That okay, how many times do I need to call someone who is at the remote location? Maybe that kind of the thing.
Hmm. Yeah. So, um, yeah, you can think of it that way that there's some function that needs to be computed, and one party has a part of the input, the other party has the other part of the input, and now they have to compute the value of the function by doing as minimum calls or exchanges as possible. So, to generalize this problem, what is really happening is that this is think of it as a function from x1 to xn and y1 to yn bits. I'll maybe write it on a fresh page. So, what is really happening is that f is a function from 2n bits to 1 bit, and we want to compute f of x comma y, but um, Alice knows the function, Bob knows the function, but they don't know the entire input. So if Alice knew both x and y, she could have just computed it. Similarly for Bob, but Alice only knows this first half of the input. Bob only knows the second half of the input, and now they want to compute f of x by doing as minimum exchanges as possible. And now, like, your point is that do as much of local computation as possible and try to compress the amount of communication that is made by computing as much as possible locally, which is what happens in this case. Alice basically finds out her part of the answer, Bob finds out his part of the answer, and finally they just do a little bit of exchange. But something like this can't happen in equality, because there is I mean, the information about x says nothing about y, because these could be maybe Alice's string and Bob's string, they agree on n minus 1 bits, but then they differ in only 1 bit. That could also happen, and we would still have to report that they are not equal. So there's nothing local about it that Alice can do to get any information about Bob string. So these are very intuitive examples where we can visualize this, but functions can be more complicated than that, and in those cases it's not clear whether I mean, what the protocol should do.
Like say if X has uh, like in the previous example, so Alice can compute the number of ones in her string and
um,
communicate the number of the ones to Bob.
hmm,
And if Bob's do the computation locally
hmm,
and find the number of ones in his string.
hmm,
And then if both are same, then probably they can go for the exchange of the sequences. Otherwise, they can declare that yes, the strings are not same. So at least instead of communicating n number of the bits, even though in the worst case quite possible that I mean the communication complexity could be of I mean would be requiring n number of the bits. However, in many cases, I mean this strategy may result lesser than n number of the bits to be transferred to be exchanged.
Right. So, yeah. So in this case, no matter what the input is, you are always exchanging n bits. But if we change the protocol and let's say you share partial information, for example, we could even do parity. So just Alice computes parity, sends it to Bob, and if the parities don't match, then the strings can't be equal. But then again, there could be worst case situations that happen if we try to save on the number of bits. But the complexity measure that we define is that in the worst possible case, this is the number of bits that we will end up using. So we defined it as the, yeah, for example, our, even in the case of our Turing machine, there could be inputs for which the machine runs, does not really take polynomial amount of time, it takes logarithmic amount of time, but there could be some very few inputs that are bad for which we do require polynomial amount of time, and we still say that uh, the algorithm or the problem takes polynomial amount of time. So similarly, there could be cases where a particular protocol saves you on the number of bits, but the way we define the measure is that we always look at the worst case scenario and say that is our communication complexity for that protocol.
Yes, but then why did we add 1 year? I mean, so this thing greater than or equals
So
to n plus one. Why not exact n?
because at the end we said that we want Alice and Bob both to know the answer. So if we don't send this answer, the step 3 where Bob has computed the answer and sends it to Alice, uh, then Alice would not know the answer, right? If we don't allow this communication.
Yes, I understand. Yeah,
So
thanks.
it's just I mean a standard setting that we have defined. We could also study uh, define games, this communication complexity games, where both of them did not know the answer, one of them knowing is also fine. So those kinds of things are also studied.
Yes, yes.
Okay, so I think we'll maybe I think it in the upcoming week or something we might be looking into this in more detail. But the point that we were trying to make is that um, that there are these games for which we have this protocol. So what do I mean by protocol being explicit? This is an example of an explicit protocol where we know what Alice does, what Bob does, and these are the things we can do beforehand, or we can hardwire it in some sense. So if we have that, we can go to an explicit circuit, and this is just a high level thing that I'm talking about. We'll probably get into the details later on. So just to answer this question, why this explicitness is I mean, does it have any consequences? That's the question. If I understand, like, I mean, of course, we're curious, but are there any implications of that? So, yeah. So there are cases where if you have this circuit explicitly, you know, this AND gate fits into that OR gate and so on, then you can come up with these explicit protocols. And now, once you have these explicit protocols, for example, if you show lower bounds like this, um, I mean, there are several jumps that we are making. So we are going from circuits to communication to implications on this, on the problems of this kind. So there are several bridges that are there, which yeah, which I didn't define yet, but um, yeah. So just to answer that, it's not just that um, it's not just a curious question, but it does have a lot of implications, which we'll probably do it in the upcoming week.
Okay, okay. Yes, yes. Thanks.
Okay. So, okay. So yeah, so this is what we did last time. We saw that these two definitions are actually equivalent, and we also saw that there are undecidable languages in sorry there are undecidable languages in P/poly. So, and the example that we saw was the unary halting problem. Okay, so can we similarly say that L/poly contains an undecidable language, where L is our class of um, languages that can be solved by a log space Turing machine, and poly is the amount of advice that is being given to the machine.
Yes, so last time you told the difference in between the Oracle Turing machine and the Turing machine wherein we are taking advice. And you told a very crucial difference, and somehow I forgot that difference. I'm trying to recall it. So probably that would mean that, as far as I remember, you told that this Oracle in the Oracle Turing machine, uh, the the Oracle gives us, I mean, establish the membership in 1 minute time. So there, the membership is being, I mean, is established. And however, in
Exactly.
the case of this PY poly kind of a thing, the we get the advice and advice. So still, I cannot recall the concrete difference.
Right, right. So, okay. So let's just go over that argument quickly. So we showed that unary halting problem is in P/poly. In fact, it is in P/1, where you only need one bit of an advice. So what is the halting problem? It's the set of all m comma x such that m halts on x, and we know that this problem is undecidable, and the unary halting problem is basically that instead these encodings are in 0 1 to the n, 0 1 star. Instead of that, we are going to encode it in 1 star. Okay, so that means the UHP is still not decidable. Okay, and then our idea was that to show that UHP is in P/poly. So how did we do that? Or let's say P/1. So how did we do that? We said that the advice that we are going to give is that um, and if the input or I'll call this the input to UHP is an n-bit string, whatever the n is. So okay, and the advice function, what it does is if x is in UHP, then um, or let's say 1 to the n halts on. Okay, so it's basically the membership. So okay, so yeah, so think of h as just telling you the membership of the problem, and um, what this machine does is that it just looks at h. If h tells you to accept, it will accept. If h tells you to reject, it will reject.
Yes. And yes,
Okay,
now I recall. But so does this mean that in the case of the advice thing, we would be using, I mean,
we'll be
I mean,
using
same advice would be used for the same problem, or there could be different advices as well.
by same problem. Do you mean input or
So I mean input for all the inputs, the same advice would be used, is it?
so we define this h to be a function from n to 0 1. So if the input is I mean in this case all the inputs will have different size because it's a unary problem, right? Um, so the way we defined edge is that for all inputs of same length, there is same advice. Okay, but in this case, there cannot be two inputs of the same length.
Yes. Yes.
So, yeah. So anyway, for one input, there will be only one advice in this case because we are in the unary world.
So I'm not asking specific to this problem. So my query is number one, the difference between Oracle Turing machine and then uh, the Turing machines wherein the advice is available. And the second thing is that when will this advice vary? If I change, because this advice is of polynomial length only.
Hmm.
And so if this advice is of polynomial length only, it is a kind of the support, extra support or a hint. But so in the case of the PY poly, the definition says that problem is decidable by the deterministic Turing machine, and wherein a advice of the polynomial length is also available. That is what the meaning of the PY poly is, or something else. You wrote the definition in the beginning.
Hmm.
So my query is that will this advice remain same across the problems, or because the PY poly class definitely would be the collection of the languages, so collection of the problems.
Hmm.
And
Right.
so for each
So,
language, do we have a separate advice or what?
yes. So, um, okay. So, this is the collection of languages for which there is a machine M, um, and we should also write there exists an advice function h. So h could be different for different languages.
Yes. S would be different for, I mean, different languages, and this advice won't depend on the size of the problem, is it? Or say within a language, if I have different instances,
Hmm.
within a problem, if I have different problem
Hmm.
instances,
Hmm.
so will this advice change or will it
Hmm.
remain the same?
So for different for the same language, we look at different inputs. For all the inputs of same size, the advice is going to be the same.
Oh, so if I change the input size, then the advice will
May
vary.
may change, yeah. But within the same input size, the advice is going to be fixed.
So I mean, this is something very happening at the multiple levels.
Hmm.
So first we have uh, individual advices for the individual languages,
Correct. It's
and
similar
language.
to it's similar to the fact that for different languages you have different machine. Similarly, I mean along with the machine you also allow the advice to be different.
Yes, yes. And for a machine, for the different input sizes, do we have the different advice? Like,
So the
like,
advice does not depend on the machine, right? Because it only depends on the input size that is given. I mean input to the language.
okay, now
So
I
you can
understand.
think of this as m of x comma h of x.
Oh, I see. So can there be the case that for the two different languages
Hmm.
and for the same input length, can we have the same advice?
Yeah, that is perfectly possible. It could happen. In fact, it could also happen for two different languages. We have exactly the same advice function, because
Oh,
the machine could be doing something else. Even though h of x is same, the machine may be internally doing something else to decide whether to accept or not.
okay, okay, all right, yeah, fine.
Okay.
So that question was asking that L by L slash poly and was asking that
Where is that? Okay. Hmm.
the question is not clear. We'll have to
Okay.
scroll
So,
down, right?
yeah. So, this is the proof of the fact that there is an undecidable language in P slash 1. The question is, are there also undecidable languages in L slash poly?
So that would mean that still the polynomial advice is available, and however the Turing machine will run in the
In
would
logarithmic
be
space.
occupying logarithmic space. So if the Turing machine is occupying the logarithmic space, then would be occupying the polynomial time. And if the Turing machine is occupying the logarithmic space, then would be occupying the polynomial time to some extent, even though L is there inside the NL, and then NL is there inside the P. But still, I mean, this L and NL would be there inside P only. So if L slash poly contain an undecidable problem, so this P slash poly contains undecidable problem. So what about this L slash poly then? So if P slash poly contains the undecidable problems, uh, okay. So can we have undecidable problems within L slash poly as well? So what if we do not have any undecidable problems in L slash poly? So that would mean that uh, so, but so by the way, what is the circuit equivalent definition of P slash poly? That this comprises of all the problems wherein we can form the circuitry of the polynomial size. Is the definition. So
Yeah.
then, yeah, if this is the definition, then L plus poly would mean that circuit wise.
Uh,
So by common sense says that yes would contain undecidable problems, because if L slash poly does not contain undecidable problems, and L is a subset of the P. And even if the Turing machine is taking only the logarithmic amount of the space, but then would then be consuming the polynomial amount of the time. So therefore, I think that this would contain an undecidable problem.
yeah. So indeed, L slash poly contains an undecidable language, and we can explicitly show that there is a language. In fact, it's the same language, the unary halting problem, and the proof is also the same. So, in fact, the same argument actually shows that this is in L slash 1, um, which is stronger than saying that it is in L slash poly, because I'm only using one bit of advice. So, how does the proof go? Well, the advice function remains the same. So it's basically encoding the membership of UHP problem. If the input is in UHP, it tells 1. If not, it tells 0. And now what our decider M does is that we M of x comma h of x, or it's not really h of x, it's h of length of x, because the advice does not depend on the input itself but on the length of the input. Okay. um, yeah. So now what this machine does is that it basically looks at what is the h of x, and it is going to output this. Is exactly what it does, right? If h of x were I should really call it h of length of x. Okay, so if h says 1, then we're going to accept. If h says 0, then we are going to reject. Or I mean, I should write it that way. If Okay, this is exactly what the machine does. Now, um, I mean, there's no computation that was involved in this. It just looked at this parameter and decided whether to accept or reject. So it's running in polytime, but also, I mean, log space is also a very um, weak way of saying it, right? Because it's not even using log space.
Yes, yes, that's right.
Yeah, so it's the same idea. Just wanted to make an observation.
So what about the circuit equivalent? Say, so what the definition used to be the P slash poly, the circuit equivalent definition, that it is a collection of all the circuitries having the polynomial size or something else. What was given?
So um, I don't think this is. I mean, it won't directly follow because. So how did we go from P slash poly to circuits? This was.
So P slash poly used to be more or less same as the P size. And then this piece, the definition of the P size used to be the collection of all the circuitries wherein the size is polynomial or something else.
Yeah. So how did we do that? We had this decider M, which takes H and this advice, and then um, decides whether to accept or reject. So, um, so how did we get these circuits? Is through the um, so what was this NP complete thing that we saw? Cook-Levin reduction. Yeah. So we used the Cook-Levin reduction to convert our machine M, the deterministic machine M, into not just deterministic but also deterministic polytime machine M, to convert this into a circuit. If you remember, this is what we did when we showed that SAT is NP complete, or circuit SAT is NP complete. What we said is that you look at any language L which is in NP, and there is a decider. By definition, there is a decider M. um, for all x, there exists y such that M of x comma y accepts if and only if x is in the language, and this is a deterministic polytime Turing machine. And what we did was we converted this into a circuit such that the circuit is going to output 1 if and only if x is in the language, otherwise it will output 0. So there was a series of steps that we followed there, which was looking into locally at 3 cells at a time and converting it into circuitry. It's the exact same reduction which will take our polytime Turing machine M, which takes these two inputs and convert it into a circuit for us. And then furthermore, we'll observe that in fact this circuit is actually of polynomial size. So this will show that any language in P slash poly is contained in P size circuits. Similarly, the other way around is also true. So how is this direction fine?
Oh, that's just another move. So it's okay that I mean this plan would this is okay, but then how to do this logarithmic part here? Like say L plus poly. So L plus poly
Huh.
would mean what?
So yeah. So um, yeah. So what I'm saying is that in this case, I mean the way we did is that we went through a series of observations and then saw that P slash poly is contained in P size, and the other way around also holds. But um, I mean A similar thing is not, as far as I know, a similar thing is not known. But if we want to think about it, let's say um, L slash poly. So let's go through the same series of reductions. Okay, so uh, yeah, what is the class of circuits that it would correspond to? Mm, hmm, hmm, hmm. So
So my point is that this L here actually does not add much value because this L would mean P in time only. So probably this L
uh,
slash poly would be same, more or less same as P slash poly. But then can there be difference somewhere?
so that depends on um, whether L is separate from P. So if L is separate from P, then L slash poly may contain languages. P slash poly may contain languages that are not in L slash poly.
But then in the relationship of L, NL, and P, we do have a rigid boundary. Like we used to say that L is there inside NL, and then NL is there inside L and NL both are there inside P.
Right, but do we know whether it's similar to the P versus NP question, right? So um, we know that P is contained inside NP, but we don't know whether P is strictly contained inside NP. Similarly, we know that L is contained inside P, but we don't know whether this is strictly contained. So, are there languages that can be computed in polytime but require more than log space?
Right, right. Yes.
So, it's not clear whether answer to this would imply. All we know as of now is that L slash poly is contained in P slash poly. We don't know whether it is strict.
Yes, yes. Yeah, right.
So, I mean, in this case, we have a nice characterization that these can be characterized by the circuits that have a polynomial size. But in this case, I think it's not very neat, or at least it's not been studied. But that's probably because you can always change a language here, you can always change the advice here and ask what kind of circuits um, these are. But I'm not sure if this is known, but maybe the way to go about it could be that look at this reduction carefully and see that instead of giving the machine polynomial time, if you give it logarithmic space, then are there any peculiarities about the circuit, whether it
Yes.
has, yeah. So maybe the details are in the reduction that
Yes,
this does.
I remember you told me introduction, and when we used to look towards the left and towards the right. And see.
Yes,
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 that used
yes.
to be very, very rigorous.
Okay. Mm, okay. So, yeah, so just to conclude, what we know is that there are undecidable languages in P slash 1 bit of advice. Okay. And, okay, I'm not sure how. Okay. Okay, let me just decide what question to do next. Mm, okay, let's try this one.
Okay.
Mm,
So it says that if NP is not equals to P, uh, or prove the following dichotomy result. If NP is not equals to P, or PS is equal to this thing.
huh. So either this is true, that P is not equal to NP, or pH is contained in the second level of polynomial hierarchy.
That if what relation, then we prove that what if NP is equal to P? But then what is the relation between these two things? That we need to prove that either NP is not equals to P or P is contained in the second level of hierarchy. Sigma 2 would mean that there exists something such that for all these things, this is true. So this seems to be somewhat similar to the Karp theorem thing, but that was in the context of this P by poly and not this case. Actually, this
So,
problem statement is not that clear.
okay, um, so what we are saying is that we want to show that, so we are not showing exactly that, um, I mean that P is not equal to NP. This is something we don't know, but we are saying that at least one of these is true, that either this happens or this happens. So independently, we don't know answer to any of these.
Okay. So
But
either of them, either we know that P is not equals to NP, or we
or
know that.
yeah, one of this has to be true. So
So
these kind of results are actually called dichotomy result, where there are two conjectures, and what the kind of statements we make is either that happens or this happens. One of them is true.
okay. And so to prove this thing, can we move in this direction that what if the P becomes equals to NP thing?
Hmm.
So if P becomes equals to NP, then what would be the situation to this pH?
Exactly. So this is,
So, yeah,
yeah, this is same as proving that if P is equal to NP, then pH is equal to sigma 2.
uh, yes. So if P is equal to NP, if this happens, so then uh, if this happens, so if this happens, then that would mean that P is a subset of this sigma 2 P. P is a subset of NP, and then NP is a subset of this thing,
Hmm.
sigma 2P, and NP is a subset of this pi 2P as well, that kind of a thing.
Hmm.
And so if that is the case, and if P becomes equals to NP, then things will collapse. So if it collapses, so then sigma 2P becomes equals to the pi 2P.
Hmm.
And if that becomes the thing, then all the higher levels will also get collapsed. So then this entire pH hierarchy will get collapsed. So probably
Exactly.
one side we could prove. What about the
Yeah.
other side?
That is enough, right? So case one would be that, say P is not equal to NP. Then our statement is already true. That we wanted to show that either one of this is true, and this is, let's say, actually true. Case 2 would be that we know that P is equal to NP. In that case, we showed that pH collapses.
Yes.
So this is done. So in fact, without using the definitions of the hierarchy and the collapse, you can also alternatively um, use the theorem that you mentioned. So alternatively, you can say that by Karp-Lipton theorem, we know that, um, yeah, we know that. Um, Sorry, what was the, mm, if P is not equal to NP, no, it says that,
There was something related to P by poly as well. I vaguely
P is,
remember.
yes,
I
yes.
forgot it. Yeah. Yes,
Uh,
yes, this one. Yeah, right. NP
if
is better.
if NP is contained in P slash poly, uh, then
Then this
then
yes,
this
then this
collapses
pH
to
collapses to this thing. Yeah.
sigma 2P. Yes. Okay. And we can do the same kind of analysis. In this case, we will assume that NP is contained in P slash poly. Then by the theorem, we know that pH is contained in pH collapses to sigma to P. Case 2 would be that NP is not contained in P slash poly. Then that means there are languages in NP which are not there in P slash poly, and in particular we know that P is contained in P slash poly, so therefore there are languages in NP. And L is not in P, so that would imply that P is not equal to NP. So in this case we use the definition of the
But then this P should appear in completely inside this FP.
right, you're right, yeah. So yeah.
What are some of those problems? I mean, how to show that there are problems in FP and which.
Sorry, I couldn't hear you.
So yeah. So, but then how to show that there are problems in NP, and for those problems, we cannot have a circuitry of the polynomial size, or which problems are there which cannot be solved by the deterministic Turing machine with the polynomial advice. Yes, there would be many problems that even the advice won't help to solve by using the DTM. Yes, this is true. This is true, and we do not know. Yeah. So that would mean that if NP is the subset of the P by poly, that would mean the deterministic Turing machine becomes so very powerful if we give some advice. And that would be same as the non-deterministic Turing machine. So, I mean, the determinism with the advice would be same as non-determinism. And but then this is seems to be so very hypothetical. Why so? Because if I view this polynomial as as some kind of the cheat sheet or some kind of the guidance given by the examiner to the student, that okay, I am going to take your examination and this is you can use this sheet. So, but then can this setup replace non-determinism? Wherein the student is seeking the advice of the Almighty that, okay, Almighty, tell me whether should I put mark C as the correct answer or D as the correct answer. So it seems that, I mean, both the setups are not equivalent. So this seems to be very hypothetical. And does this have relevance? I mean, so much relevance that, I mean, how can people think of that NP be contained in P by poly? Or can be contained even can be contained even. I mean, this would be equivalent as replacing the non-determinism by the determinism plus some advices.
Yeah. So yeah. So on one hand, you have non-determinism as your I mean something extra that you have, and on the other hand, you have this advice, and we don't know which is more powerful. So
Yes.
in fact, popular belief.
Yeah, non-determinism should be more powerful, isn't it?
Well, we saw there are undecidable languages in P slash poly, which I mean, whereas NP is a class of decidable languages. So, I mean, it's not. I mean, it kind of seems. I mean, this could also be more powerful. Whereas on the other, I mean, you have two different kinds of um, powers that are there. So we don't know which is more powerful at the moment. But yeah, but generally this is the popular belief, and that would imply that P is not equal to NP, which is also common belief.
Yes. Yeah, I got this point. Yeah. Thanks.
Yeah, but okay, I'll just leave this question for you to think. Maybe we'll not go into the details of it, but we saw that HP is not decidable, is not in D, and then we converted it into this instance of UHP and showed, and we know that this is not in D, and we then showed that UHP is in P slash poly. Okay, but let's say that I look at SAT, and SAT is in NP. Now if I could show that SAT is in P slash poly, okay, then this would imply that NP is contained in P slash poly, right? Sorry, this is P slash poly.
Yeah. So set is, if you could show that set is the element of this thing, uh, then yeah, right, true.
True. So I just want you to observe that why can't we do the same thing that we did earlier? So from this instance of HP, we converted it into a unary instance. So why can't we do this, that take the SAT instance, which is a binary encoding, convert it into unary SAT instance, which is just take the binary encoding and represent it in the unary encoding, and we know that USAT should be in P slash poly by the same argument. What it will do is it will look at the membership of USAT, that is basically the advice function is just that tells you the membership, and you're just going to accept or reject based on whether it says 1 or 0. So USAT by the same logic, same exact same steps, USAT is in P slash poly, in fact P slash 1. So why is it true that UHP in P slash poly implies this semi-decidable undecidable languages being in P slash poly, whereas even showing that USAT is in P slash poly does not imply that NP is contained in P slash poly. So there is a small detail to observe there. Um,
Yes. Yeah.
Okay, so just think about it, because if this part is clear, then that means you've like understood it really well. So I'll just let you think about it, and if you want to discuss this, we can take it up next week. But it's just a
Sure, sure.
very small detail. Okay,
Yes, yes.
and okay. So um. Okay, so this is again a very small tweak in the argument that we saw here. Okay, so how do we see that P slash poly is same as P size? One direction is that you use the Cook-Levin reduction to show that a language in P slash poly has a circuit of polynomial size. The other side was easier, to show that a language with poly size circuit is in P slash poly, because will give as advice the circuit itself. So we know that this is a family of circuits. Okay, so the idea was that in this poly sized advice that we are allowed to communicate, we will give the description of the circuit, and once you have the circuit, the evaluation can be done in polynomial time.
Yes.
Yeah, so okay, so by the same idea, we want to show that P uniform P size is contained in P. In fact, it is true that these are equal. So let me define what this class is before I. Okay, this is true, but we will not show the entire proof. We will just show one side of the proof. Okay, so what does this P uniform P size basically mean? It says that um, if I give you um, yeah mm, okay. Okay, so if I give you um, this circuit family, okay, then for a given n you can uh, compute this C. So input will be an n, and you can compute this Cn in polytime. So this is where the P comes from. Okay, that the circuit can be computed in polynomial time for a given n. So one by one, for different values of n that you give, we will be able to come up with the explicit circuit Cn and altogether get this family of circuits. Okay, so and P size is basically that each of these Cn's is poly-sized circuit. So this is more restricted than P size, because we have this additional property that it satisfies, that given n it can be computed in poly size. The Cn can be computed in poly size. Therefore, because this is more restricted than P size, we are actually showing something stronger, that it's not in P/poly but rather in P itself. So is the definition of the class P uniform P size clear?
So P uniform is not that clear actually.
Okay.
I could understand till this P size, but then what is uniform here? Uh, that is
Hmm. So, uniform in the sense that we know that uh, what does this uniform basically signify? So, earlier we saw that Turing machines are, um, I mean, okay, let's say circuits. Let's look at circuits. So, circuits are non-uniform model of computation, because we don't really have one circuit solving the problem, but we have a family of circuits solving the problem. Therefore, we say that they are non-uniform models.
yes.
Okay, and now what this P uniform is signifying is that um, if you um, if you can compute these circuits in polynomial time, given n, you can come up with the corresponding Cn in polynomial time. Then, um, with respect to this, I mean, with respect to this property, we sort of have the circuit rather than
Oh, yes.
relying on the family.
Yes, yes. So if value of n is given, then such a circuitry can be constructed in the polynomial time,
Hmm.
and this will bring a kind of uniformness,
Hmm.
at least that okay.
Hmm.
Uh, yes, and that would be the subset of the P.
Hmm.
And so, since we can construct the things in the polynomial time, uh, and
Hmm.
so that would mean that for all inputs, for all inputs, the circuitry can be made in the polynomial time. So we have on one side we have this thing, and the other side we have all the problems which are decidable in the polynomial time. So decidable and this thing, I think would be a subset. And why can't we write it as equal? Equal would also be fine. That if we can build the circuitry for every problem which is there in P,
Hmm.
I can construct the circuitry in the polynomial time. You give me an input and then I will find the circuitry in the polynomial time. Because I can solve the problem in the polynomial time, so therefore I am able to construct the
You
circuitry in
will,
the polynomial time. This seems okay. I mean, there is no, yeah,
yeah, yeah, yeah. But this direction is very obvious, because I mean, it's easier, because to argue this, we are simply saying that, sorry, I should write P size here. Okay, to argue this, we are saying that the input to us is x, okay, and let's say length of x is n. Then what we will do is, we know that it is P uniform, so I can use this algorithm and compute the corresponding Cn in poly time. That is our step 1. And now that we have this Cn, we are going to run x on Cn, and basically we are computing Cn of x. Okay, and if Cn of x is 1, then we are going to accept, and if it says 0, then we are going to reject. This is the algorithm which runs in polytime, because this step can be done in polytime and this step can also be done in polytime, and the third part is just to decide whether to accept or reject. Therefore this entire algorithm is in P. But okay, to see the other way around, we will need to use that we just need to rely on one fact, that from a deterministic polytime machine we can go back to a circuit of poly size, and additionally the fact that that this is computable. So the Cook-Levin will basically tell us that from this decided this sorts of tables that we had, we can come up with there is a family Cn, but also use the fact that we know how to explicitly compute such a function. So if you give me an n, there's an algorithm which follows this Cook-Levin steps to compute the Cn exactly.
Yes.
So that will show that P is contained in P uniform P size. It's again the same idea, but just one more observation. Okay.
Right. Yes.
Okay, there's one more question about P poly, but I'll leave it for now because I just want to cover a few other topics, but I'll just state the question. We'll not solve it right now. Okay, so S here is a subset of 0, 1 star, and which is basically a subset of all possible strings, and you say that S is sparse if so you can think of S as S0 union S1 union S2 and so on, where these are the strings of length 1, S2 is the strings of length 2, and so on. Sk is the strings of length k in S. Okay, and so how many strings are there that could be of length k?
So there would be 2 raised to the power k number of
Exactly. I'll call this n for okay. So there could be 2 to the power n many possible strings of length n, but I'm going to impose the restriction that you are not allowed to have too many strings of a particular length. So S intersection 0, 1 power n, we are going to restrict the size by saying that the maximum length that I'll allow for this is polynomial in terms of n. Okay, so all possible strings are not allowed, and this restriction is there for all of them. So for every length n, you are only allowed to have polynomial p of n many strings of that particular length. So if this happens, then we say that the set S is sparse.
Yes.
Okay, and what this question asks to show is that if S is a sparse set, then S is contained in P/poly. So basically you have to come up with an advice, a poly bit of advice, such that given that advice there is a deterministic polytime machine that solves this. In fact, the other direction is also true. So
But then what would be the solution of this capital F? What would be that solution? It's
for
okay.
this,
Yeah. So this S is a Schwarz set, and out of the total number of the subsets possible, total number of the sets possible, we have put we have imposed some kind of the restriction. So now, I mean, so what is S? S is a sparse set. It's okay, but what kind of this problem is, and I mean, what is to be shown that this problem is problem formulation is not clear. Actually,
Okay.
S is the sparse set, it's fine, but then what would be the membership? Say if I say that X is the element of set, X is the element of capital S, what would it mean?
So S is nothing but a language.
Language. So that thing is not coming. S is the language. It's the field. What kind of language is it?
So any language L is a subset of. So if you recall, we said that L any language L is a subset of 0 1 star,
Yes, yes, it's
and
fine. Yeah. Uh,
and whatever, I mean, and basically it's L0 L1 and so on, right? So whatever strings are there that appear in this set, those are the members of the language, and the rest are not. So I mean, if I just write L in terms of S, I think that would clear the question, the doubt.
so it's I could understand this now. When I see that you wrote this S2 as the intersection of S and with this 0 comma 1 and the square. So basically, at every point, the things are getting restricted, not this entire thing. Oh yes, so we need to show that this is the element of P slash poly, and with the polynomial amount of the advice, we should be able to decide the thing.
So
Please.
actually the other direction is also true, that sparse sets are exactly same as P slash poly, but the reverse direction is slightly involved. This part follows from definition.
Yes. So I
Huh.
can I give the
Yeah, yeah.
advice in the form of like say for SN I can give advice that you just check that whether what is the cardinality of S is the cardinality of S is smaller than this amount, say 2 raised to the power n kind of. So if this is true, then certainly the membership can be decided becomes decidable by the determination theory machine. Because everywhere we would like say for S2, we want that there should be less than 4 number of them.
Huh, um, uh, but what is the input that is given to the instance? It is some string of length n.
Yes, yes.
Okay. Now, using just that particular string, you want to check whether it is an actual member of the language or not. So even if you somehow find the count, that count doesn't tell you whether this particular string that is given is a member of the language or not.
Oh, yes. So, but then if a string is given to me, at least I can determine that whether it belongs to S0 or S1 or S2,
Correct. Correct.
based on the length
Correct.
thing. And once I reach to once I pinpoint to that set, and now I would be requiring some advice to show that whether this indeed is belongs to this set or not, or is outside this thing. That would be required. So for that thing, but then how to decide that this is not that thing, and I mean because S2 is constructed by taking the intersection of S with 0 comma 1 square. So quite possible that whichever string you give me after deciding that okay it belongs to S2, but how to show that this is not the common, this is not the common string, and this is the uncommon one. So if that is the case, then this is very difficult because uh, how would I know that this is very difficult? So
So
seems that this may become undecidable, but then how to show that this becomes undecidable? That uh, uh, it would be there in P slash poly in the sense that we would be requiring polynomial advice. So what that advice be? Advice
Exactly.
could be like
Hmm.
USP, and even though I was not happy with that advice, but then you can give him the advice like, okay, you check that whether this string is there at the intersection of uh, this s and 0 comma 1 whole square or not.
Hmm. So that advice will not work now because um, let's say you have some input of length 0 1 to the n, and you want to check whether this x is in s or not, and you want a p slash poly. I'll go for this. So now if the advice function cannot be the membership of so advice h of length of x says 1 if x is in s and 0 otherwise. This can't happen because let's say uh, there are, okay, I'll write it here. So what are all possible strings of length n? All, let's say all zeros, one of them is 1 and so on, all the way up to all ones. These are 2 to the n many strings, out of which some subset of these are actually in S, the rest of them are not. So if x is actually a member of this set, then this advice should say 1, otherwise it should say 0. But notice that h does not depend on the exact value of x, it depends on the length of x. So there could be some x of the same length which is outside S and another x of the same length which is inside S. So this advice is very confused because there could be instances of same length but having different memberships. Why this worked for unary is because there was only one string of a particular length.
Yes, yes, yeah, it's clear to me. Yeah, thanks.
Okay, but your answer is somewhere close. Like, I mean, um, so what this advice should do, you've identified it correctly, that it should tell you the membership of that particular string. Okay, now you can't carry one bit of advice because of this particular constraint. But notice that you are not allowed to have one bit only, right? You are allowed to have p of n much advice. So you could be storing lots of information there. For example,
Yes.
can you store all the strings that are there in S of uh, length n?
So to store all the strings of the length, and I would be requiring exponential here. That one for 2 raised to for a particular SN. But then for a
But
particular S, I think that there would be polynomial number of
exactly. Hmm.
yes. So if there
So
are polynomial number, then I can store it.
correct. So that's the answer. So what you are actually going to do is h of length of x is actually going to store all strings of length that are there in S. So we know that this is bounded by p of n, and each of them is an n bit string. So totally this is how much advice we are actually using. This is basically,
Yes,
yeah,
yes,
p of n many strings, each of length n.
yes.
So that's basically the advice, and what the algorithm will do is that it will uh, look at this entire advice and think of it in terms of blocks of length n and check whether the input x matches with any of these. If it does, then we will accept. If it does not, then we will reject.
Right. Yes, yes.
Okay. So that shows this first part, and if you can show that the other way around is also true, that is p slash poly, I mean all languages in p slash poly are sparse. If we could show that, then part B is direct.
So I need to show that the other direction, and the other direction is that all languages in P by poly are the all languages. This is then all the languages in P by poly are the sparse. So even in the P by poly there are undecidable problems as well. So this will
This
then
will also mean that undecidable languages, the not it does not say that all undecidable languages are sparse, right?
yes,
Yeah,
yes.
there are some undecidable languages in P poly, and we know for sure they are sparse.
Right. So, yeah, and all the languages. So, I need to show that for all the languages wherein the polynomial advice is going to work along with the deterministic Turing machine. So, better I solve it from the scratch. I mean, at the level of the Turing machine. So, does this mean that all the deterministic Turing machines which I can think of and which would be taking the polynomial advices can be represented as the sparse sets? So, there is a small Turing machine and with the polynomial advice available. So, a Turing machine would be evaluating basically, would be accepting a language. And whichever language the Turing machine accepts or decides would be the subset of the Kleene closure of sigma you just mentioned. So that would indirectly be the intersection of this thing. Intersection of what? Say I have a Turing machine and which has got state 2. But then how to enumerate the things? How to enumerate that a Turing machine? Because even with the two number of the states, I can have a Turing machine and that would be uh, accepting a string and which is very, very long. So because I wanted to show that that Turing machine, out of the many possible languages, Turing machine accept a specific decides a specific language, and that specific language is equivalent to this one element of the sparse set. Because this one element of the sparse set is what all possibilities and intersection with. See, I mean, this
So,
sparse set is this thing. Uh, I mean.
uh, so,
Sparse set. Yeah.
so this is not the collection of all sparse sets. By the way, I mean, we are just saying that. So, if L is in P poly, then for all n, L intersection is at most P of n for some P, some poly. So, and therefore L is sparse.
So, but then this is true. This is true. Where is the issue here? Because any language, a language is what? So if L is the element of, uh, but then the language could be an infinite collection as well. But it's okay. But even though the language is an infinite collection, but then every element of the language is finite. A string is always of the finite length. So if a string is of the finite length, so if I take the intersection of L with this thing, then definitely this is going to be less than this P of thing, the polynomial thing. So L is sparse, L is sparse, L is sparse.
No, so how do we know that there are only polynomially many strings of length and in our language?
Oh, so polynomially many strings and which are there in the language. Because this L is because this is I mean L is the element of P slash poly, so it will be decidable by a Turing machine and which runs in the polynomial time. So if the Turing machine runs in the polynomial time, then the length of the string itself cannot be. infinite. I mean, length would be finite only, and that would be of polynomial length.
But uh, can't there be, can't this polynomial bit of advice, why can't L be, let's say, sigma star?
Oh yes. So L could be sigma star, no issues in that. But then when I take the intersection of L with this thing, I would be picking one string of the L and taking its intersection with 0, comma 1 and cleaning closer. Oh, sorry, N.
Hmm.
And all the strings which whose length is less than N, their intersection thing is going to be null. Say for example, nothing would be common. Oh, common. I mean, common would mean that what? Okay, yes. So all those strings. But then every string of the L is the element of the clean closure of sigma. It's okay. But then every element of L would be of finite length and polynomial length. So if I take
But
its intersection with 0, comma 1 raised to the power n, that would be polynomial length,
but
isn't it?
it's about the number of strings that are there in the language of that. But so I don't know what is wrong with this example, but it seems to contradict. But let's say L is sigma star, okay, then if you think of it as L0 union L1 union L2 and so on. So Ln, you want L intersection 0 1 to the n to be P of n for L to be sparse, right? But in this case, because L is sigma star, it contains all possible strings of length n.
Uh, See, if the string is of the length less than n, and if I take its intersection with 0, comma 1 and raised to the power n, so that will result
Ah,
into that string only. But if the length of the string
uh,
is so, say if you
no, no,
consider the
no, no.
union,
So if you take a string of length k, which is less than n, your claim is that
that would be of its intersection with 0, comma 1 raised to the power n
hmm,
would be equals to k only. Length would be equals to k.
this will be phi, right? Uh, because this consists of all strings of length n,
Yes. So,
where
and this intersection will give the common things.
but
So
this is
therefore,
uh, but I mean it does not. So this particular thing is a string of length k,
yes, yes.
but I mean uh, so for example, let's say k is 2 for us and n is 3, and so on this side what I'll have is all these all these elements. Now what is the intersection of this string into this set?
So that would be equals to 0, 1 only. The original string is back. So you take intersection. What is common?
What is
Common,
common in
com.
elements? So
Uh,
uh, so when you say S1 or A intersection B as sets, that means it is the set of all elements x is in A and x is in B.
yes, you are right. So in that case, if k is less than n, so then the intersection would be equals to 5. Nothing would be there. But if
Hmm.
uh, but if n is but if you consider all n plus ones, so then also it would be equals to 5.
It will be 5, but we are
5.
only interested in this
This thing.
this particular case. Yeah.
So in the case of the Ln, I mean this intersection will make sense only if the strings in L are of the length n only.
Hmm. Yeah.
And for those strings clearly, I mean that the length of the intersection is less than or equals to q. This is true.
This is not true because if L is sigma star, then all of these are full, right? In the sense that it contains all the strings of length 0, all the strings of length 1, and so on, all the strings of length n.
Okay, but if you take the intersection of these many strings with 0, comma 1 and it raised to the
Hmm.
power n.
Then this will be
it will filter out only those strings which are of the length n.
which are of the length n, but those are 2 to the n many strings.
So yes, yes, oh yes, yes,
So
right.
although we want this for sparse set, but if L is sigma star, then what happens is that L intersection 0 1 to the n is nothing but this size is nothing but 2 to the n, which is clearly not poly. So my confusion that arised now while describing this is that so L seems to be a language which is not sparse, right? So L should not be in P slash poly, but since L is sigma star, it's trivially in P. So there should be something wrong with the claim. Right, so okay, just to write what my confusion is. So if L is sigma star, then we know that L is not sparse. This is something we observed just now because it contains all strings of each length. But also L is trivially in P, therefore L is also in P slash poly. So this seems to contradict the claim that we have here.
Yes.
So maybe I'll check once again if it is that maybe like this is some corner case that's that's excluded from the claim, or whether there is some issue with the claim itself. So I'll check this out.
Yeah, yeah, sure, sure. Yeah.
Okay. And okay, so let's end the discussion of P slash poly with that. I'll quickly talk about this class called RNC. So in the circuit complexity world, we saw classes AC, NC, and so on. So you know that NC0 is contained in AC0, it is contained in NC1, AC1, and so on. This is an infinite hierarchy, and AC is the union of all this circuit, NC is the union of all the NCI circuits. And these were the two major classes that we saw. And I think at some point you asked whether there is non-determinism that can be associated with these classes. So although the non-deterministic version model is not studied or is not explored, there's a randomized version of this class. So R stands for randomized NC.
Yes, yes, randomized.
Yeah. So how do we define this? We say that F is in RNC if, so think of the circuit as taking the input X as well as it is taking some additional random bits. I'll call it R in 0 1 to the P of length of X. Okay, so if length of x is n, then you are allowing p of n many random bits that the circuit can take. Now, yeah, if you can come up with a circuit C which takes x and r as its input, and um, f of x is equal to 1, then the probability over r that the circuit CXR is equal to 1 should be at least half. This is very similar to the RP class, and if f of x is equal to 0, that is x is not an instance of, is not a 1 of f, then q want to be correct always. Okay, so recall that in RP what we had was that if x is in the language, you want to be correct with at least half probability, and if x is not in the language, then you should always be correct. So in this case there should not be any error. So okay.
I have a query here that at this point the randomness is probably seems like as if the randomness is included by some compulsion. Compulsion in the sense that both circuitries are independent of each other. Like say the
Both circuit
circuitry
as
which
in
is circuitry which is meant for the original string X is the traditional circuitry which we have studied so far, and this another circuitry has been added in sequence, wherein we are computing this value, and depending upon whether the circuitry because these values are random, so whether the circuitry computed this value as 1 or with this thing. But there is no impact of these random bits. I mean, these random bits are not mingled, are not intermixed with the input. So if they are not mixed with the input, then how would we truly, utilized this randomness feature? Because in the randomized algorithms also what happens? In the randomized algorithms also we generate some random input, and but there also I think that in all such cases this randomness is separate
separate
from
from
the
the
input
input. Yes.
and is indirectly affecting the input, and it's not like that as if we mix the randomness with the input and then let it flourish, along with the input and give us something. Oh, I understood. Yeah, this seems similar to RP in this context at least. Yeah.
Yeah.
And
Yeah.
do we have other bounded from one side, bounded from both the sides, those equivalent also for the
Yeah,
NC?
you can define um, yeah, BPNC and ZPNC and so on, similar same definitions, only yeah, with the probabilities will change, but RNC is the most studied one because it captures parallel algorithms. Okay, so so what do we mean by that? So okay, so notice that if okay, I'll just be able to give mm, a brief idea of this. So okay, one algorithm that you might have seen which is in RNC is the perfect matching problem, I guess.
Bipartite, yeah,
Bipartite.
matching.
Yeah,
Yes,
so
yes.
bipartite perfect matching can be done in RNC. Now, why is this important? Because let's say I just think of this as a problem, and you want to come up with an algorithm to check whether there is a matching. So this is our bipartite graph with two partitions A and B, and there are edges across. We want to check whether there is a perfect matching. So um, the natural algorithms that we see use the Hall's theorem and so on, check the neighborhood and so on. All these algorithms that we know are there in polytime. I mean, so I mean, there are standard algorithms that show that bipartite perfect matchings is in P. Okay. Um, but the non-bipartite case is the harder one, but we'll not be dealing with that as of now. But now, why do I care about this RNC? Is because the polytime algorithm that we have is a sequential algorithm, in the sense that here is the series of instructions that the Turing machine will perform. So this is in P, therefore there is a deterministic Turing machine M. What it does is, given an input X, it will do several series of instructions, and at the end it will tell you whether there's a matching or not. But now let's say I'm interested in parallel computation of this. So maybe that there are several processors that I have, and they are independently computing some information um, about this graph that is given. At the end, we are going to decide uh, use this parallel computation and make a decision whether there's a bipartite perfect matching or not. So this additional resource that I have, which is parallelism, is something that could be used in several scenarios like distributed systems and so on, right? So if you have different processes, can I do faster? And this RNC sort of exactly captures that. So this is the set of languages um, that have efficient parallel algorithms. When we say efficient parallel algorithms, we mean that we have P of n many processors that are running parallelly, and all together we can compute the solution in polynomial time. Or, okay, I mean, that is still fine, but should be something more that I'm forgetting, but there is a more crisp definition of this, and RNC exactly captures that.
Okay.
Okay, so therefore, okay, so to answer that, so therefore, this is something that is relevant in practice. Therefore, RNC is a more known and more studied class, but the other variants of BPNC and ZPNC and whatever we can define, they don't, or at least we don't know a natural, um, I mean, characterization of it. So therefore, this is something that's well studied. But of course, we can define no harm in, I mean, those are valid definitions.
Yes, yes. Bounded errors from both the sides can also be thought of. Yeah.
Right. So another example of languages in RNC would be checking maximal independent set. So this is different from maximum independent set. Which just says that if I so maximal just means that it need not be maximum, but the given set that I have, there cannot be more elements that I add to it, and the resultant set will still be an independent set. So whatever set I have, uh, it is an independent set, and there cannot be more edges, sorry, more vertices or elements that we can add and still maintain the property that S is an independent set. So basically, the moment you add something more, we will violate the property that it's an independent set. So it is maximal, but there may be some other entirely different set which is independent set but has larger cardinality than S. So so this maximum independent set is an NP complete problem. this reduction is from click, vertex, cover, and so on. But maximal independent set is known to be in polynomial time. So what is a natural algorithm for this?
So uh, I need to keep on adding the elements and then till I check that whether the independency is being maintained or not. So I can go for this thing greedy approach. I can use it and something similar to this MST thing, crystal kind of thing. Then I can go
Yeah.
for it. Uh, yeah, but I've not heard of this problem actually. Maximal independent set. I've heard independent set, and especially the maximum independent set, wherein we need to find the largest set of the vertices, in which none of the vertex is connected to the other vertices. But this one is seems to be interesting problem.
So in fact, every optimization problem that we uh, think of, um, okay, is either a maximization problem or it is a minimization problem. For example, we want to find maximum independent set, we want to find minimum vertex cover, and so on. Right. So for every maximum, you can convert it into a maximal question, and every minimum question can be converted into a minimal question. Okay. For example, if you want to find what is the maximum size of uh, matching, so in a graph, that is, if I give you um, a graph like this, what is the maximum sized matching here? It would be
Is this similar to wherein sometimes we use premium function and then because there could be many maximals. Maximal need not to be unique, and similarly minimal also need not to be unique.
yeah,
So
but also
sometimes
maximum at the same time maximum also need not be unique, and minimum also need not be unique.
maximum in a sense would be unique with maximum.
Mm, okay, maximum is unique in terms of the size, but there could be different
Yes, that's right.
answers. But yeah, I mean one um, yeah, the observation is correct. This is a fixed number, whereas this could be a varying number. Okay. So okay. Anyway, just to just wanted to mention that every maximum has a variant called maximal, and every minimum problem has a variant called minimal. And typically, the minimal maximal problems are easier to solve, whereas the maximum minimum might be difficult. Okay. And yeah, so in this case, the trivial algorithm that one can think of is that you have this graph G, and what we'll do is these are the vertices v1, v2, and so on up to vn. So first I'll put the vertex v1 into my set. I'll just blindly put it. Next I'll check v2 and see if it forms edges with the current vertices that I have. So if it does not, I'll add it. Then I'll look for v3 and check if it forms edges with the current set S that I have. So this is similar to the Kruskal's or Prim's behavior, that we are building it part by part. Every time check if um, I mean it's a
Yeah,
tree,
it
or
is. It is. Yes, yes.
you are
It is
right.
not going to form the cycle, right?
So
In the case of the crystal, and in this case, yeah, something else.
yeah, so it can be argued that this is a maximal set, because anything else that we throw into set, we are guaranteed to have an edge. So it is an easy argument to show that this algorithm is correct. So algorithm is just that go through each vi in V, and if vi does not form an edge with vertices in S, then S is equal to S union Vi. We'll just add it and keep on doing this. And right. So now this algorithm is clearly in P because you are iterating through one vertex only once, and this check can be done in polynomial time. Okay. So this is something that we know, but um, the behavior of this algorithm is very sequential. That is, first I'll choose the vertex v1, then I'll take v2, check if it forms an edge with any of the previous vertices, then go for v3, then and so on. So it's very very sequential. Okay, I can't parallelize this algorithm because if I do that, uh, I may end up making edges.
Yes, that's true. That's true. But I can smell some kind of the parallelism here in the sense that, like, how do we prove that this is going to result into the global solution? So, it's like in this, this is whatever strategy is being shown here. This is based on the greedy method only.
Hmm.
And in this greedy method, we show that if the things is a matroid, so if it is a matroid, would mean that if it follows two properties, that the hereditary property and then the exchange property, that if the set is a solution, its subset would also be a solution. If I have a smaller solution and a bigger solution, and I can take some part of the bigger solution and include it in the smaller solution, there would also be a bigger solution. So this thing can be parallelized in the sense that I can divide it into two or three or the multiple number of the places. And then I can go for the parallelization, because if all are independent, then I just need to combine very few of them, so as to show that yes, they are still, this independency is maintained. I think that this can be done, this can be parallelized without much hurdle.
Mm, okay. So, okay. So let's say you decide to do it into two parts. Okay, there's like say n by 2 partition that we do. For this, we um, will parallelly. Uh, I mean, solve this independently, and now join the solutions. But now there may be edges that come up. So what do we do with that? Because
Yes. So in that case, if ages come, so I will not include those vertices. I will not include.
so which will
I will exclude both. I will exclude both in that case. If an age come up in between say V1 and V5, then I will exclude V1 from the first half and then V5 from the second half.
both of them.
Yes.
But then, if you do that, then clearly we are violating the fact that it is maximal, because I could now add this new vertex v1, and still this will be my maximal independent set.
Oh, so instead of omitting both, ignore one. I
Ignore
mean,
one. Okay. So if we do this, hmm, if we do this, how do we? Okay. Let's say I'll ignore v1, and I will ignore v6. Mm, then there could still be an edge between v2 and v5.
yes. So so basically, yes, 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 could be.
So that is where the non-trivial part comes in. That if you discard all of, okay, yeah, if you discard all of the bad pairs, all the vertices, then you may violate the maximal property, and if you discard arbitrarily one of them, then it may not be an independent set. So uh, there is still some processing that needs to be done to make sure that we are still maximal and also maintaining the independent set. So we have to choose the right set of vertices for that matter, but the idea of the initial idea is actually correct. That is how it proceeds. The RNC algorithm for this, although will not do it, because it involves you can look it up online, though it should be available somewhere, but if you are interested, um, yeah, the idea is actually going to be very similar, that we are going to think of several parallel processes that are happening, solving it independently. Now when these problems come up, we will uh, exclude some vertices also. Okay, also these are not like arbitrarily chosen, the sets. There is some probability associated with it, so with some certain probability we are going to pick the vertices into our set, and then when this bad sort of thing happens, we'll discard it and repeat the process over. So I mean, the whole um, correctness that in the end that particular algorithm will give us a maximal independent set relies on the parameters that were chosen in the probability. So I'll not go into it, but the point that I just want to make is that there are algorithms that are very serial in nature, and we want to show that they are in RNC because we want to um, obtain parallel implementation of it. And this is just one example. Also, this is not as simple as so the analysis of this was slightly simpler because um, yeah, because we observe the permutations that
So can we discuss this in the next class, because I have another session at 8:50.
oh, sure,
Yes.
yeah, yeah,
Thank you so very much. Yeah.
yeah, sure,
Good
okay.
night.
So
Yeah.
I'll
Thank
be
you so much.
uploading this in the yeah in the YouTube. Okay.
Thank you so
Yeah,
much.
thank you.
Good night.
Good night.